Imagine cracking an egg into a bowl and violently mixing it until the yolk and white become a single, uniform liquid. If someone asked you to reverse that process, to perfectly separate the original yolk from the white, it would be impossible. Once the ingredients are entirely blended, the physical laws of entropy make the process irreversible. The cosmos we live in today is that fully mixed egg. The sky is filled with mature stars, complex galaxies, and massive black holes. They are the final, blended product, hiding the original state of the early universe. Fortunately, physics offers a workaround. Light has a strict speed limit. Because it takes time for illumination to travel from one place to another, looking deep into space is identical to looking back in time. The further away an object is, the older the image we receive. While we cannot literally unscramble the universe, we can look far enough into the deep void to see the egg before it was ever broken. To see that infant universe, we built the James Webb Space Telescope. JWST is a massive, highly sensitive infrared observatory designed specifically to act as the ultimate cosmic time machine. This diagram shows a wave of ancient visible light traveling across an expanding grid. As the universe expands, it stretches the light waves, pulling them from the visible spectrum into invisible infrared. Webb's mirrors catch this stretched light, a process known as redshift. In 2022, astronomers pointed Webb at a tiny, dark patch of sky. They expected to find a slow, quiet-forming universe with scattered gas clouds slowly pulling together. Instead, they found thousands of ancient galaxies. These thousands of ancient, mature galaxies represent a direct challenge to the established timeline of the universe. This timeline not so be accepted standard model of the universe over its 13.8 billion year history, moving cleanly from the Big Bang to the first cooling gas, to the first stars, and finally to mature galaxies. Gravity is a weak force. It takes hundreds of millions of years for vast, cold clouds of hydrogen gas to gradually pull together and eventually ignite to form the very first stellar structures. The JWST deep field data reveals massive, fully formed galaxies existing a mere few hundred million years after the Big Bang. The universe produced mature, highly structured cosmic cities billions of years ahead of schedule. Deep inside the centers of these early galaxies lies an even more difficult problem. They harbor supermassive black holes. This diagram illustrates the Eddington limit. The Eddington limit is a strict physical threshold that dictates exactly how fast a black hole can consume matter before the intense radiation it generates pushes the incoming gas away, effectively cutting off its growth. Even if a black hole started feeding at the absolute maximum allowed speed the second the universe began, it could not gather enough mass to reach a supermassive scale in such a short window. It hits that hard physical ceiling long before getting big enough. To solve this, scientists have proposed the direct collapse theory. In this model, massive gas clouds bypass the star phase entirely and collapse straight into giant black holes to explain their presence in the early universe. The early universe is bypassing its own physical laws of growth, forcing astrophysicists to theorize entirely new mechanisms just to explain what they are seeing. This chronological error persists even at the smallest scales, down to the microscopic behavior of atoms. This chart displays the exact ratio of the first elements forged in the early cosmos, a process known as Big Bang nucleosynthesis. The calculations predict a universe made of roughly 75% hydrogen and 25% helium, numbers that match our observations today. But those same calculations also predict a specific trace amount of lithium. When scientists measure ancient stars, they find only about 1/3 of the lithium that the model expects. From supermassive black holes down to trace atoms, the timeline of the universe simply does not match the physical evidence. Does all this conflicting data mean the Big Bang theory is wrong? Decades ago, physicist Georges Lemaire first proposed that the universe expanded from a hot, dense state. That insight became the foundation of the hot Big Bang model, and it remains the most robust scientific framework we have. The continuous expansion of space and the faint afterglow of the Big Bang, the cosmic microwave background, prove that the foundation of the model is solid. We aren't throwing the theory away, we are stress testing it. The Big Bang model stands, but our assumption of a slow, simple, and quiet early universe was completely wrong. The infant universe was not waking up slowly. It was incredibly dense, fiercely active, and defined by chaotic, high-speed collisions. Telescopes like JWST are built to do exactly this: break outdated models to force a better understanding of the cosmos. The universe isn't a static number, it's a living story. We know the middle, we know the end, and right now we are finally rewriting the missing first chapter.